All right, we'll let people trickle in here. All right, we can probably go ahead and get started as people continue to come in here. So I would just like to say hello, everyone, and welcome to EPSP Connects. My name is Scott Feehan. I'm a PhD student at the University of Nevada, Reno. And along with my co-organizers, Udita Mukherjee, Claire Masteller, and Joel Scheingros, we'd like to thank you for joining us here today. And as some of you may know, EPSP Connects is a monthly seminar series that alternates between wide-ranging panel discussions and scientific talks. And before we dive into our presentation today, I would remind you all of upcoming seminars on October 14th and November 18th, with details on the slide here and also more information available on our website. And as per typical Zoom seminar protocol we've all become familiar with, the chat will be disabled during the presentation and open back up at the end for questions. And so it is my great pleasure today to introduce Dr. Helen. Helen got her start at the University of California, Berkeley, where she received her bachelor's in integrative biology. Following a number of years working as a biologist in various environmental consulting and restoration roles, she moved on to the University of Oregon, where she received her master's in geography. She earned her PhD in geology in 2019 at the University of Nevada, Reno, where her dissertation work involved in part understanding the dynamics and evolution of river basins. And during that time, she was a mentor to me, so this introduction is extra special. And since then, she has moved on to a postdoc with the Earth Surface Dynamics Group at ETH Zurich, and today she'll be presenting her work entitled Complex System Response to External Forcing in Bedrock Rivers. And I'll let you take it away, Helen.
Great. Okay. Thank you, Scott, for the really nice introduction, and thanks to the EPSP Connects organizers for putting together this great series. And I'm really excited to share with you what was a large part of my dissertation research on complex system response to external forcing in bedrock river networks. So, so what do we mean by complex river system response? We know that bedrock rivers evolve in response to tectonics and climate, with different conditions producing different steady state fluvial relief. And we know that when tectonic or climatic conditions change, transient changes in elevation move upstream in a wave-like manner to bring both the channel and the surrounding landscape to an equilibrium state. We also know there are transients in the planform geometry of river systems, with a wealth of studies in a range of tectonic settings documenting changes to river network topology, dating back to Davis's 1889 paper, where he documented this river reversal that I'm showing here. We can visualize these two different types of transients using a landscape evolution model. So here, I'm showing an animation of a simulation where every point on the landscape experiences a pulse of rock uplift. And in response, the river networks in size, bringing the entire landscape back to equilibrium. You can see that divides, which are shown with higher elevations in brown, remain in about the same position through the simulation, despite the fact that there's a pretty large tectonic perturbation. This simulation shows a simple response to forcing in that changes that occur in one river basin do not affect the adjacent basins. We can also look at a simulation primarily with transients in planform geometry. So in this simulation, differences in the distribution of drainage area among adjoining river basins results in these river basins eroding at different rates. These differences in erosion rates then push the water divides to bring the planform geometry to equilibrium. So here at the bottom of the domain, you see shorter rivers eroding more rapidly and moving the divide towards the top of the domain. Rock uplift and rock erodibility are steady and uniform here. So all the rearrangement that you're seeing is purely a result of differences in basin geometry. This is a complex response as opposed to a simple response in that any change in the size and shape of any river basin necessarily impacts the size and shape of all the adjoining river basins. And these interactions can then have cascading effects by creating additional transients in planform and in profile. So in this talk, I'll go through how this transient behavior appears in nature. To do this, we'll look at 3 landscapes. So first, we'll look at the Ozark Dome, an ancient landscape where we might expect divides to be static. And then we'll look at the Sierra Nevada, California, which is a rejuvenated landscape, so we might expect to see an incisional response. And last, we'll look at the high plains, which is transitioning from depositional to erosional. So we expect to see both incision and geometric adjustment. So I mentioned that river network reorganization has been documented for over a century, but it wasn't until recently that we had the tools and the data to examine it at these regional scales. The foundation of these tools is the geometric parameter chi, which can be derived from any model of bedrock incision that results in slope area scaling. Here, I've used the stream power model of bedrock river incision. So at the top, we see an equation for the time rate of change in river elevation z. And then we can solve this for steady state, assuming uniform rock uplift u and k, rock, the constant for erosional efficiency. We get the equation on the bottom left for steady state river channel elevation, where chi here is the upstream integral of essentially 1 over drainage area raised to the river's concavity, with A naught being just a scaling parameter that gives chi units of length. So chi is this really key geometric parameter of a river network. It is a distance upstream scaled for drainage area. It's a proxy for steady state river elevation. So we can see in this first equation that it scales linearly with steady state elevation. And it's also a time. So it can be converted to the channel response time for a perturbation if we include k in the integral. And if k is relatively uniform, we can think of chi by itself as just a relative time. Because chi accounts for changes in drainage area with distance, we can use it to transform river profiles. So when we plot chi against elevation for a river network that is in equilibrium, all elevations collapse more or less to a straight line. So we can use deviations away from linear as a sign of transience. The slope of the chi plot, whether it's in equilibrium or not, is the channel steepness index, which is a measure of erosion rate. We can use chi as a proxy for steady state river elevation to map planform disequilibrium by coloring river networks by their chi values in what we call chi maps. So when 2 basins are in geometric equilibrium, as I'm showing here, across divide channel heads have equal elevation and chi. All elevations in the rivers collapse on one line in a chi plot, and all divides are symmetric. When 2 basins are in geometric disequilibrium, across divide channel heads have unequal chi, as is shown here on the right, with the lower chi basin in green pulled to the left of the steady state line on the chi plot, and the higher chi basin pulled to the right of the steady state line. The elevation of the channel head with lower chi is higher than the steady state elevation for that chi value for these tectonic and climatic conditions. So it will erode faster than the background uplift rate. The elevation of the channel head with higher chi is lower than the steady state elevation for that chi value. So it will erode slower than the background uplift rate. And it's these differences in erosion rates that are what drives the divide to migrate. So we can use these characteristic patterns in chi maps and these characteristic forms in chi plots as signatures of area exchange. But these signatures may look really different depending on how the network is adjusting. So today, I'll talk about what I found to be the three main landscape states of geometric transience. A landscape state where continuous divide migration dominates, a state where discrete geometric change dominates, and a state where network replacement is occurring. So in landscapes dominated by continuous divide migration, river capture and the resulting large transients in river profiles are rare. But instead of seeing these discrete changes, there are continuous perturbations to topography and channel profiles. And as a result, river profiles and topography will reach a quasi-equilibrium state in which river profiles deviate from linear in a systematic way that reflects ongoing area exchange. And then likewise, asymmetry at divides also reliably reflects the direction of divide migration. So this is a state that's most likely to occur in landscapes without big transients in channel elevation or geometry, or after the bigger transients have worked their way out of the system. In landscapes dominated by discrete geometric change, frequent captures create large transients in river channel elevation, as I'm showing here in the chi plot on the bottom. And as a result, river profiles won't approach an equilibrium state, and the topography at divides may or may not reflect the direction of divide migration, as further topologic change is likely to occur before the topography can really adjust to any capture. So this landscape state is one in which we expect to see large transients in both and river channel elevation. The most extreme state of geometric transience is complete network replacement. So this is where an inefficient network is being replaced by a new network, often essentially a replacement of one landscape with another. So the most clear example is that what occurs along large escarpments. So this brings us to the first case study, the Ozark Dome. So the Ozarks are a structural dome that was uplifted in the late Paleozoic, and there's no evidence of any disturbances to the river network occurring since then. So given this stability, traditional geomorphic theory would predict that the landscape would have reached an equilibrium state. But what we see is that the river networks are in geometric disequilibrium. So here I'm showing a chi map for the Ozark Dome, where the white lines represent the major drainage divides. And you can see that there are large differences in cross-divide chi across many of these major divides. So this suggests that the modern river networks are adjusting in the direction that I'm showing with the black arrows to bring the network to geometric equilibrium. But are there dynamics here that actually impact landscape morphology? To test whether divides are actually moving, we measured erosion rates using beryllium-10 in paired basins, such as this pair. So here I'm showing the erosion rates. Those are the numbers on the map. And you can see that in this example, the erosion rates corroborate the predictions made with chi, or that the basin with lower channel head chi, painted in yellow, is eroding faster than the basin with higher channel head chi. And that this results in divide migration towards the higher chi basins. You might be thinking those numbers aren't that different, and you are right, but they are different by an order of magnitude greater than the error. So we measured erosion rates in 8 pairs of basins with similar lithology and in a range of disequilibrium across the dome. The locations of these basins are shown with the black markers on the chi map. And in each of these pairs, we also measured the difference in cross-divide channel head chi. So on the right, I'm showing a plot of the resulting data where each point here represents a pair of basins that share a divide. So on the x-axis, we have the negative difference in chi, And on the y-axis, we have the difference in erosion rates. And what we found is that in all pairs, the basin with the lower channel head chi is eroding faster, like what I showed in the previous image, or that in all cases, the divide is moving in the direction predicted by geometric disequilibrium. I want to point out that we intentionally don't try to fit a line to these data, as it's still unclear what the expected relationship is. And we see large cross-divide differences in chi, but only really pretty small differences in erosion rates. So this implies that the river networks here are moving towards equilibrium, but very slowly. And that implies that divide migration has likely been a persistent phenomenon in this landscape. We see evidence of continuous divide migration in channel profiles as well. So this is just one example of what a lot of the profiles in the Ozarks look like. We see really asymmetric basins when there is a difference in channel head chi anyway. And of course, the channels are different lengths, so it's not surprising that they look asymmetric in the untransformed longitudinal profiles at the top here. But what we see in the chi plot is that they are relatively straight and they nearly collapse, but that they deviate from each other in exactly the manner that we would expect by the difference in channel head chi, with the lower chi basin being just slightly steeper and pulled to the left, and the higher chi basin being pulled to the right. And likewise, where we see equal cross-divide chi, we see perfectly symmetric river basins, and the profiles collapse on the chi plot. We looked at the comparison between topographic asymmetry and geometric disequilibrium a little more quantitatively by measuring mean basin slope and channel head chi at a drainage area of 10 kilometers squared in paired basins along many major divides. So here I'm plotting the difference in mean basin slope on the y-axis, and again, the negative difference in chi on the x-axis, with each point again representing a pair of basins that share a divide. The black markers show pairs where there's no geomorphic evidence of stream capture, and the red markers show evidence where there is geomorphic and topologic evidence of stream capture, namely one large capture that runs through here, a proposed capture anyway, it's not confirmed. Anyway, what we found is that basins with lower channel head chi were systematically steeper than basins with high channel head chi, except in cases where there's stream capture. These systematic differences in slope are the most striking when we look at land cover in the Ozarks, in that the land is the flattest and, of course, therefore the easiest to farm in basins that are losing drainage area. So we can see that the boundary between the forests and the farms traces out the boundaries between a basin that's gaining drainage area and a basin that's losing drainage area. Although we don't see a lot of river captures in the Ozarks, we do see a few, and I'll use this example of a capture on the Ozark Dome to explain how captures trigger positive and negative feedback. So here we propose that the blue basin, the basin here painted in blue, captured the headwaters of the basin painted in red at the point shown by the yellow star, with a plot in the middle showing the current modern topology, where the basin painted in blue has gained drainage area and the basin painted in red has lost drainage area. We can look at a simplified schematic of a chi plot to see how this capture then brings these main stems closer to equilibrium. So if the open red marker is the original channel head for the red basin, it's lost elevation, drainage area, and length, which lowers its chi value. If the blue marker is the original channel head for the basin painted in blue, it's gained elevation and then gained length and drainage area, and therefore its chi value has increased. So the difference in chi value between the current channel heads has been reduced. The tributaries to these main stems don't experience changes in drainage area directly, but they experience changes in base level fall. So with the tributaries of the basin that's gained drainage area, these experience an increase in the rate of base level fall, and the tributaries to the basin that has lost drainage area experience a decrease in the rate of base level fall. So in this way, captures create transients in channel elevation. Captures also create further geometric transients. So tributaries don't experience changes in area or length, like I said, but their chi values change because chi is an integral value, and so changes in drainage area downstream in the main stem, downstream of the junction, impact the chi values in the tributaries. So looking again at a simplified schematic of the chi plot, if the open black marker is a tributary channel head, if it's a channel head to the basin that's lost area, its chi value increases. And if it's a basin of a tributary to a channel head of a tributary to the basin that's gained drainage area, its chi value decreases. And so the difference in chi between these two channel heads has increased. The effect is positive feedback that then promotes further area exchange between the two basins, which we can see in the chi map here and in the topography in the hillshade. The most dramatic example of how landscape morphology can be shaped by persistent non-uniform erosion rates and positive feedback is the in situ formation of elevated low relief surfaces. So zooming in on this basin here in the northern Ozark Dome, we see that chi predicts this basin to be losing drainage area or to be experiencing ongoing drainage area loss. And then we can look at a relief map for the basin, and we see that the boundary of the basin traces out a region of anomalously low relief. Looking now at an elevation swath profile across the basin, we see that the entire basin stands about 100 meters higher than the surrounding terrain. And then when we plot chi against elevation, we see that the interior rivers, which are painted in red, show the characteristic signature of losing drainage area, and the exterior rivers, or rivers that drain the flanks of this surface, which are painted in blue, show this characteristic signature of gaining drainage area or being pulled to the left. Comparing erosion for two streams internal to the surface with two streams draining the flanks confirms that the divides are indeed migrating inward and that the basin is indeed shrinking. So this shows that localized relief can grow in the absence of localized rock uplift, and that in a low relief landscape like the Ozarks, this mechanism can actually result in some of the dominant landscape relief. But with this difference in erosion rates, it would take 35 million years to generate the observed relief, which is a long time. So that suggests that what we see in the Ozarks is that the broad morphology is shaped by really persistent, continuous divide migration over tens to potentially hundreds of millions of years. So in summary, in the Ozarks, we see slight curvature in river profiles, slight asymmetry at divides, rare captures, and a few elevated low relief surfaces. So these observations imply that the landscape has reached a quasi-equilibrium state, or a state in which river channels and topography deviate from equilibrium systematically and in a manner that's consistent with ongoing drainage area exchange by continuous divide migration owing to disequilibrium in river basin geometry. So on to our second case study, the Sierra Nevada. The Sierra is an ancient mountain range formed in the Mesozoic. Its modern form is strongly asymmetric in cross-section with a gentle western slope and a steep eastern escarpment. So for this study, I looked at rivers draining the gentle western slope, which is also shown here on the map on the right, enclosed in a red line. There's considerable debate about whether or not the Sierra has been uplifted in the late Cenozoic. So in today's talk, I'm just going to focus on the fact that it is experiencing late Cenozoic incision. Here I'm showing relief for the western slope of the Sierra. It's turned on its side here, so the crest of the Sierra is along the top of the map. And what we see is that deeply incised main stems cut through what's otherwise really pretty low relief terrain. Comparison of stream incision rates, which are on the order of 0.1 millimeters a year, with erosion rates from upland surfaces, which are 1 to 2 orders of magnitude lower, demonstrate that the morphology here really reflects a state of transient incision during the late Cenozoic. In addition, volcanic deposits cap modern interfluves in the Northern Sierra, as shown with the brown here. And it's thought that these deposits once blanketed the Northern Sierra and likely filled and smoothed pre-existing topography. So now looking at a chi map of the Sierra, to the left of the thick dashed line, we see large differences in chi across many of the divides in the Northern Sierra, coincident with the remnants of the volcanic deposits. These differences in cross-divide channel head chi indicate that the river networks in the Northern Sierra are in geometric disequilibrium. So to look at how the combination of geometric and elevational transients impact this landscape, we will zoom in here to a representative portion of the Northern Sierra. So the first thing we can notice is that there's no obvious spatial patterns in chi or relief at the basin scale. So unlike what we saw in the Ozarks, here there's no pattern. So if we follow the main divide here, separating the Middle Fork American from the South Fork American, we see no coherence in cross-divide differences in chi. And there's no changes in topography across the divide either. We can examine this in detail on a piece of this divide. So here I'm showing the results of the awesome divide tools by Forte and Whipple 2018, looking at a handful of metrics for divide stability. So on the top, we see chi, that chi predicts the divide is unstable and will move to the south, like we can see in the chi map. And then the 3 metrics that look at modern topography, relief, elevation, and gradient predict the divide to be stable. Looking at 2 profiles that originate on this divide, we can see a huge transience in the long profiles and in the chi plots. And if we think about chi as time, we can see that the transient will reach the divide of the basin painted in blue much sooner than we'll reach the divide in red, implying that eventually the divide will move south. We can look at another pair of streams that originate on the same divide, but this time in the interior of the larger river basin. And we see a case where topographic asymmetry across the divide is consistent with the differences in chi. So the basin painted in blue has small tributaries with low channel head chi and high relief, and it's appears to be migrating inwards to the basin painted in red with higher channel head chi and very low relief. And we see extreme asymmetry in both the long profiles and the chi plots. So what's really striking in the Northern Sierra is that we have to look at the scale of individual river channels to see where divide topography has adjusted to move the network towards geometric equilibrium. So we interpret disequilibrium at this scale to reflect a much younger perturbation to the river network. And this appears as both transients in channel elevation and planform geometry. Along with divide migration, of course, comes river captures, which you see in the Sierra dissecting the network both at minute scales, like I'm showing here, and at much larger scales. So here, I'm showing one of the larger river captures in the Sierra, where we propose that the Bear River once reached the divide and has since been captured by the South Yuba River. We can look at a chi profile or chi plot of these 2 basins, and we see the characteristic signature of river capture with a captured reach that has approximately the same slope in the chi plot as the victim basin, and the Nick zone in the South Yuba extends just slightly above the modern elevation of the Bear River. At the proposed capture point, we also see a beautiful wind gap with a meadow in the Bear River that suggests a much larger river once flowed through here, or that erosion rates have significantly dropped here with the loss of drainage area. So using these topologic and topographic markers of capture, We mapped proposed captures in the Sierra, and we found them to be very prevalent in the Northern Sierra, where we see geometric disequilibrium, and much sparser in the Southern Sierra. As I showed in the Ozarks, the most dramatic impact of drainage area exchange on topography occurs in basins where they're experiencing ongoing drainage area loss. So in the Sierra, we see it most clearly in these three basins, which I'm highlighting. And these have very high channel head chi compared to their neighbors. And then we can look at relief calculated over a 1 kilometer window. And we see that these basins trace out large regions where relief is really low and uniform. But in contrast to the Ozarks, where we saw kind of a similar thing, but we saw a dramatic difference in both elevation and relief at the basin boundaries, here we don't see striking asymmetry across the basin boundaries at all. And we interpret this to mean that area exchange by stream capture is dominating, and that the distribution of erosion rates in river basins has been too dynamic to create asymmetric divides. So to summarize, the river network in the Northern Sierra is in geometric disequilibrium, coincident with the direct disruption of the network by volcanic deposits. We see incision of the existing network at the largest drainage areas, but discrete geometric change, it really dominates at the smaller scales. And we interpret this to reflect a landscape state in which the largest transients in channel elevation and geometry are still really working their way out of the river system as a result of this fairly recent perturbation. Lastly, looking at a landscape where reorganization completely dominates the incision of the existing network. So the high plains were formed when a wave of dynamic uplift sweeping westward generated a large amount of erosion off the Rocky Mountains, which buried the region of the high plains in alluvial megafans. The wave of uplift continued to sweep westward and uplifted the high plains. And then at this point, deposition switched to erosion. And then what we see today are that the remnants of these megafans, which are called the Ogallala group, and I'm showing here on the map in blue, what we see is that they've been significantly eroded from both the western and the eastern edges. And then looking at a chi map of the region, we see large regions with anomalously high channel head chi. And these regions correspond perfectly with the remnants of the Ogallala group. Zooming in here to the Arkansas River, we can see that the river network is bifurcated into two domains, with dendritic rivers draining the Rocky Mountains, and then poorly integrated rills, or kind of a linear river network, draining the fan surface. Looking at these two channel structures side by side, we can really see the lack of network integration on the fan surface, which results in the river network having little erosive power compared to a branching river network. So although we saw a high degree of disequilibrium in the Sierra, it mostly occurred as these small pockets within larger basins at the channel scale. Whereas here we really see these two large domains. So I call your attention to the scale bar here. 100 kilometers is the width of the Sierra Nevada. So this is a much larger scale here. Using a combination of stream incision rates and river channel metrics and an analytical solution for an advecting river profile, we estimated that the escarpment separating these domains is migrating at about 2 to 20 millimeters a year, so really fast. And this suggests that as the escarpment migrates, it captures large swaths of the fan surface and transforms these linear rills into a dendritic channel network. Looking at a chi plot for the Arkansas River, in which the data is colored by these two domains. So black points here represent channels part of the dendritic channel network, and gray represents channels that are part of the poorly integrated rills on the fan surface. And we can see that channels in the Arkansas River separate out into these two distinct domains, with channels on the fan surface having very different and distinct profile shapes. But it's clear that they've been captured from the fan surface. We can look within the Arkansas River Basin at a mobile escarpment that separates dendritic channel network from parts of the fan surface that have then already been captured, to see how the network on the fan surface is being transformed into a dendritic channel network. What we see is that the channels on the captured fan surface do not appear to simply experience incision of the existing network, but rather what we see is that the channels are dissected via numerous tiny captures, and in doing so, the topology is essentially totally reconstructed. So to summarize our understanding of the evolution of the high plains, we can compare it to a modern megafan on the eastern side of the Andes. So the top left shows a chi map of this Andean megafan, and the top right shows again the chi map of the high plains, with the fan deposits being shaded in tan. So of course, the chi map, the entirety of the portion of the megafan in the Andes is shaded in tan. And then the bottom panel here shows simplified schematics of the proposed evolution. So the left image shows the state of the rivers on the modern megafan, with non-branching rivers that flow directly down the regional slope. So we can think of this as an initial condition for evolution following the cessation of deposition. And then the image on the right shows the modern state of the high plains, with dendritic rivers having replaced the linear rivers as this fan surface is eroded at both the channel heads and the toes. So to summarize our findings in the high plains, what we see is that with this extreme geometric disequilibrium that resulted from transition from a depositional surface to an erosional one, this resulted in complete reorganization of the river network, or essentially reestablishment of an entirely new river network. In conclusion, river networks can be thought of as a complex system with coupling and feedback between the planform and channel elevation response. And second, geometric transients can take different forms, from catastrophic to continuous divide migration. But what we really see is that there are landscape scale trends where different forms of adjustment really dominate. And then lastly, given the long time scale for achieving geometric equilibrium, it may be more common for landscapes to be dominated by geometric disequilibrium rather than geometric equilibrium. And with that, thank you very much. And I'll take questions.
Awesome. Well, thank you, Helen, for such a great talk. So we'll go ahead and open up the chat now for questions, and we'll let people go ahead and type them in there. But as we wait for that, I actually have a question regarding the talk, and it might be very specific, but in your Northern Sierra section, you showed the extent of Pleistocene glaciation. And I was just curious if you explored that influence on network reorganization in the upper reach of your rivers.
Yeah, no, the answer is no, but I don't notice an impact. Most of the disequilibrium really occurs more in the foothills. And it's really coincident with the current remnants of the deposit. It's similar to the high plains in that it's almost has to reconstruct the river network in those areas. But in comparison, like the largest rivers are really re-incising in their what I assume, some of which is their former network.
Awesome. All right, well, thank you for that. Let's see. You can go ahead and you can type your question, or you can raise your hand, and if you would like to, we can unmute you, and then you can ask your question that way as well.
We have a question. Hi, I'm Udita. We have a question from Kai Hu, and we have a question from Kai Hu, and he or she's asking, could you talk a bit more about the quasi-equilibrium state? Is it a state close to actual equilibrium?
Yeah. So I think it's approaching equilibrium, but I think the point is that it's really never going to approach, it's never going to reach equilibrium. It really, the profiles are still transient, they're still in disequilibrium, right? They just reflect this continuous perturbation. So instead of seeing big transients, you see this kind of continuous adjustment. So, I mean, I think it's close to actual, it kind of just depends on what you refer to or what you think of as equilibrium, right? The erosion rates are all about the same, you know, they're all the same order of magnitude. They deviate very slightly, but they are different, and they're different systematically in a way that is consistent with geometric disequilibrium. So I'm not sure if that answered his question or his or her question. Maybe they want to respond.
So we can move on to the second question here from Joel Peterson. And the question is, likewise in the Southern Sierra, you state that the uplift field is complex and chi is incorrect. Could you expand on this?
Sure, yeah, I mean, I didn't really talk about the Southern Sierra at all in this talk, but yeah, I mean, when there's large changes in the uplift field, so the Northern Sierra, even if there is an uplift gradient, it most likely is higher at the crest and lower at the foothills, or lower at the mountain front. So when you're integrating chi, that you can still kind of compare the chi values across the divides, because you're only ever looking at two adjacent river basins. Whereas in the Southern Sierra, there's the Kern River, which runs parallel to strike, and then there's a lot of faults, and yeah, it's just much more active there. So I guess chi map being incorrect is not really the accurate terminology. Chi isn't really wrong, it's just a geometric parameter, but it's more that you can't infer, it's hard to interpret. It's much more difficult to interpret when there's a non-uniform uplift field. Okay.
We have another question from Monica Rasmussen. Do you think that you could use chi maps for more detailed geologic mapping? And is the magnitude of mineralogical differences in, example, the Sierras, large enough to account for smaller scale chi variations across divides? She also adds that due to erosion rate differences. Should I?
I don't think so. I think there's too much going on in the Sierras. So yeah, no, I think the differences in chi are not caused by lithology. They're caused by the geometric disequilibrium. So I don't think they could be used to map mineralogical differences.
So Aaron Steelquest asked, how do you think the timescales of moving towards equilibrium act with the timescales of changing climatic regimes? As these bedrock rivers, as these are bedrock rivers, would you just assume fluctuates with time?
That's a great question. So I think the timescales of moving towards geometric equilibrium are far longer than the timescales of changing climatic regimes, like probably by orders of magnitude. I don't think that we really know. I don't think that's a, yeah, I think that's still kind of an open area of research, is what is the time scale. I think when there's large transients, such as we see in the high plains, the time scale of divides moving and captures occurring is much faster than, say, in the Ozarks. But then for actually reaching geometric equilibrium, the time scales like we see in the Ozarks are tens to hundreds of millions of years. Let's see, and then bedrock rivers, I guess we don't worry about timescales of changing climatic regimes when assessing geometric disequilibrium, but kind of one of the points I want people to take home is that we should really be looking at landscapes with both as a whole. So we should look at the geometry of river networks and transients in elevation. So if you're trying to understand a landscape for climate change or looking for signatures of climate change, we should one should probably look at the geometry as well, because everything is going to be interacting. So that's my best job at answering that question.
Yeah, we have another question from Jesse Zondervan, and it says, "Hi Helen, great talk and some convincing data. I think one big challenge is taking account of lithological complexity in some study areas. Example, it affects sky. Do you have any thoughts on the influence of lithology in your study areas, or how we might tackle this in future studies?"
Yeah, I mean, I think that is a big, not so much open question, a big area of potential research is looking at how, I mean, in some great studies, Sean Gallen has a great study looking at how lithology does impact transients in geometry. But I think a little bit more work is needed to kind of lay out how the signatures really differ. So I think in the Ozarks, I didn't state really whether where I think the perturbation to geometry comes from. It could potentially be from lithology, but when you see all the more landscape morphology really reflecting divide migration and reflecting the geometric disequilibrium, it's clear that it's not reflecting lithology. So shrinking basins aren't necessarily a whole different rock type, right? And we don't see changes in channel steepness occurring along, we see more changes in the morphology occurring with regards to changes in chi than we do with rock type. And then in the Sierra, the situation is like a lot more complex. I mean, I think the volcanics are what create the network disequilibrium. So the disruption, it was caused by rock type. And a lot of the regions with higher chi are regions where there are still remnants of volcanics, and this just needs to be eroded. But it also generates other, right? This still generates transients and repercussions and positive feedback. So yeah, I think that's a big area of research still.
Awesome. And so Sophie Rothman says, great talk, Helen. Do you think the persistent disequilibrium can help read geologic history from topography, or could it be confusing by perceiving so many signals?
Yeah, I think I guess maybe she means, or Sophie, maybe she can elaborate on what you mean by geologic history, if you mean tectonic history. Yeah, like in the Ozarks, I think it'd be pretty hard to tell. I guess I'm not really sure how to answer. I think I need a little bit
We
more
can
clarity.
unmute her if she wants to talk. Should I go ahead and unmute her?
Yeah.
We could also just move on, and if Sophie wants to clarify, she can write in
Okay.
there.
So Kristen Sweeney says, hi Helen, great talk. Can you comment on the role, if any, of heel slope processes in divide migration and or stream capture?
Oh my goodness. Great question. No, I didn't study that at all. I think that definitely, I mean, yeah, probably, honestly, I can't comment on it. I didn't study hill slope processes at all in any of these landscapes. So yeah, that's a great question. And that's another big topic of research, I think, that a lot of people are undertaking, how the divides actually migrate, how river captures actually occur. So yeah.
So from Fiona Club, hi Helen, nice talk. I was wondering if you've explored other metrics that might characterize plane-form geometry apart from chi differences across divides. I was thinking metrics like drainage density, junction angles, basin shape, basin orientation, etc., which don't assume anything about erosion.
Yeah, I mean, I don't think chi assumes anything about erosion rate laws either. It's just looks at the geometry. But no, I haven't really explored other metrics. I think it kind of depends what the goal of the study is. So, I mean, there's a lot of great metrics if you want to know whether a divide is actively migrating, right, then I think looking at the so-called Gilbert metrics are really what you want to do. As Forte and Whipple showed, looking at the modern topography of the divide is going to tell you whether that divide is migrating. But certainly, I mean, I think it just depends on the nature of the differences in geometry from what you're, and kind of the state of the geometric transients. So in the high plains, yes, we definitely see differences in density and junction angles and basin shape and basin orientation, right? But not so much in the Sierras, and not at all really in the Ozarks. In the Ozarks, let me bring up the Chi map again. In the Ozarks, we really just see some really wonky geometry, which kind of looks like what would have happened if these rivers had formed on a really flat surface and then been uplifted. And it just takes a long time to erase this topology. So it's certainly an interesting thing. That's an interesting idea to think about, yeah.
Marine Sanders says, Helen, thanks so much for the talk. Have you considered aspect-dependent microclimates, if any, at your field sites affecting divide movement?
I have not. No, but I also, that would have to be really small microclimates. And then I think we wouldn't see so much of a correlation with Chi, with geometry. But that's another interesting idea, like looking at hill slope processes, what actually drives the divides, and can these microclimates or hill slope processes change how the actual mechanisms of divide migration and stream capture. So that's, yeah, would be a really interesting thing to look at.
So from Ben Puritan, nice talk, thanks. The mountain front megafan surfaces are also pretty flat. I'm thinking of the Great Plains in northwestern Argentina, which would also lead to some linear flow path effects, particularly if you use a D8 flow algorithm, or lower quality elevation data. Are these possibly affecting the calculations, or do you not know artifacts when looking in the field / satellite imagery?
Well, yeah, there are definitely some artifacts from flow routing. A lot of the high plains, or some of the high plains, at least the southern high plains especially, let me find this slide. There aren't even really river networks. Here we go. There's actually just a lot of playa lakes, but it's really this stark difference in erosion rate that is still driving it, right? Whether or not some of the flow routing is artifacts or not, it's still not a stable setup, right? It's not going to be stable for long periods of time like that, especially with a dendritic river network and a steady state elevation for the landscape that's lower. So I don't think it really impacts our interpretation. It certainly impacts parts of the Chi map, but I don't think that really impacts, yeah, our interpretation that there is wholesale network replacement going on.
Awesome, and it looks like, unless somebody wants to throw in there, that they are typing a question real quick. Awesome, so I think Ed and wrap it up today. I just want to, oh, actually, just kidding. We have one more question coming in here. So it's from Bidya and Yadav. And so any thoughts on using Chi metrics for catchment classification?
I don't know what catchment classification means. Sorry, can he or she clarify? Can they clarify? Or do you guys know what that means? I don't know what that means.
Unsure, but let me see. Bidya, we can unmute you if you want to clarify further, or if not, that's okay too. You can also type whatever works.
Yeah, I'm unmuting myself. Thank you. My camera was closed, so. Hi. Yeah, so basically by catchment, like you can classify like water sets for different things. So I'm thinking in terms of, I'm thinking mostly in terms of hydrology. So how does, like different kinds of catchment, let's say I have different flow characteristics such as terms of time of concentration, things like those. So if there is some, this is a new thing to me, like, chi metrics. So just trying to get some, pick your brain. Like
Yeah.
Yeah.
Sorry, I thought you were finished. I have thought a lot about that, and I think it would be really interesting, and I want to look at it. I've talked to Greg Pasternak at UC Davis a little bit about doing that, and I think that it certainly does impact or I think it has the potential for impacting the hydrology and soils, and yeah, probably even valley width and a lot of other more reach scale characteristics. But I haven't done it and I haven't looked at it, and it would be pretty complex in that there's a lot of things going on in every landscape. And you would have to you wouldn't just have to use the chi value, but you'd have to at every point on the river network get an assessment or make a calculation of how much that basin is, a victim basin or an aggressor basin. So you'd have to take every channel head upstream and then think about the differences between all those channel heads and all the nearby channel heads to get kind of an actual estimate for that portion on the river network. So yeah, I think there's potential. I've certainly noticed it just anecdotally.
Awesome. Well, I think with that, we can probably wrap it up here as we're coming up on time. And just on behalf of everyone, I want to say thank you so much. That was an incredible talk, Helen. And we very much look forward to your work coming out in the future here. And just a reminder for everybody, there should be an exit survey as you sign out here, and also sure to register for our upcoming event on October 14th. Thank you all, and we'll see you next time.
Thank you so much.
Thanks, Helen. That was awesome.
Thank you.